So here we are, this nice old building.
Beautiful. How does it make you feel being here again? Do you feel nostalgic?
I feel as though I'm in a time warp. I've gone back 50 years in time because it looks the same. You know?
Yeah.
It's the same. You would walk in here. Let's see what we've got in here.
Wow, look at this.
Changed a lot.
Wow.
But this is where we did the search, right here.
So this is the original room where you'd be looking.
This is the original room.
Looks like no one's cleaned up since about 1959.
It looks as though it's become a storeroom.
So where would you actually
When we
sit?
were
Where would you
observing, we had a counter here, and in fact, here's the original equipment here, which was used to control the telescope.
Right.
This goes back to 1958, so
Wow,
it's
it's beautiful,
50
isn't
years
it?
old, and probably still works.
Should we turn it on? See what we get.
I don't smoke.
Is it
might
plugged
come
in?
out, I don't know.
Don't think it is plugged in.
But this is the original thing, and it was before computers. It's this whole thing, and in fact, at the time of Project Ozma, there were no computers. It was all done by eye and ink on paper tapes.
So this is the original Project Ozma.
This is the
Console.
console for the telescope control.
Right. Yeah.
Project Ozma itself had a separate
Okay.
group of equipment, which isn't, I don't see it here.
Yeah.
It looked a lot like this, but this isn't it.
And what was it like working here in 1960 when you sort of first came here as a young astronomer?
It was wonderful.
You had this telescope.
It was the happiest time of my life. It was, anything was possible. These were the first really big telescopes in America. There were already big ones in England and Australia. But the radio universe had hardly been explored, so you never knew from one day to the next what great discovery was going to come. Soon after I was here, we used this telescope to to discover the radiation belts of Jupiter, for example. That was done easily once we had the idea of what frequency to look at, and we had to build a special antenna to capture that frequency on this telescope. But we discovered the radiation belts. We measured the temperature of Saturn for the first time. We measured the rotation rate of Jupiter to an accuracy that's never been improved on.
Is it funny being back here again?
It's funny, but it seems as though almost nothing has changed. You know, it looks the way it did 50 years ago. And in a way, that's a good thing. Some things last. But this is where we conducted the search, and here's the telescope, much as it was then. The only thing that's changed is what's at the focal point of the telescope.
So what's changed now than
well,
was
what is up at the very tip of the support is now different because they're using this telescope for other purposes. But the basic structure is all the same. This is a style of telescope which is no longer made. It's called an equatorial telescope. It has one axis parallel to the axis of the Earth, around which you can rotate the telescope to counteract the rotation of the Earth. And then a second axis which allows the telescope, the dish, to move north-south.
I mean, this one must have been one of the first. When was it built?
This was built in 1957.
So this is one of the first radio telescopes, well, the first generation of radio telescopes to go up.
Well, there had been others, not quite this large, built in Australia and England.
Yes.
Right after World War II.
Yeah.
But this was the first attempt in the United States to get into the radio astronomy business seriously. And here in America, the tradition was to use the equatorial configuration, which allowed you to track things just by rotating around one axis that was parallel to the axis of the Earth. That was traditional. It worked very well. You didn't need computers. You just had to run a motor at a constant speed, and the telescope would track. So this was built that way, and that's why it looks the way it does. Nowadays, we don't use this mount because we can control the telescopes with computers as to where they're pointing.
So presumably back then, no computers, no digital technology. Someone has to be there all the time.
Someone has to be there all the time. You have to be controlling it all the time, driving it.
Yeah.
Back then, the situation was entirely different from today. the thoughts, particularly by serious scientists, of life beyond Earth were considered taboo. That was considered below the dignity of good astronomers. And this grew out of the many false claims of seeing evidence of life on the moon and on Mars. The work of Percival Lowell got a lot of publicity.
He of the Canals.
He's of the Canals and the civilization that was solving its problems with this great canal system that he thought he saw through the telescope, all of which proved to be false.
Do you think that's because sort of back then, we obviously have a sort of anthropocentric view of the universe?
It was very anthropocentric, yes.
And do you think sort of back then it was even more so than it is now? Perhaps in the certainly after the Second World War, we had a sort of self-importance,
yes.
which when we talked about things out there, or the possibility of civilizations out there, it was poo-pooed. Because I think scientists now, most scientists seem to at least accept or pay service to the fact that there probably is some sort of life, whether it's complex or not.
It's almost universal that scientists believe there is life elsewhere. What's controversial is how often does that life evolve into an intelligent technology using species. And that is problematical, and we don't have enough evidence to really get a good handle on that. That's going to have to wait until we've actually discovered some other civilizations.
I mean, given that as a young scientist being here, I guess you must have felt nervous about doing these kind of observations with government money.
I was too naive to be nervous.
But did you always have a belief that there must be civilizations?
I had a belief, which anybody who's really looked through a telescope at night for a long time would have. You see all those stars, and you learn nowadays, as you can, that most of them are like the sun. And it's almost unthinkable that we are the only ones. And then later you find out, there's another 100 billion galaxies. There has to be life out there. And I think that's quite certain. What is difficult to say is what it's going to take to find that life, because their technologies may be difficult to detect.
I remember reading somewhere that you kind of thought that by the year 2000 we would have made contact. And I think about our sort of science fiction, obviously 2001, the famous book and the famous film by Arthur C. Clarke, and then of course 2010, where we are now, which was another film. The year we made contact, and here we are, we still haven't made contact.
Well, we should have. What happened was people became skeptical, particularly people who were in charge of the purse strings, of the money. And we started in the mid-1980s to construct extremely powerful SETI search systems. And this was using government-supported, government-provided money. But in the early 1990s, these efforts were seized upon by publicity-seeking members of the American Congress, who used it as what they thought were examples of the taxpayers' money being wasted. And the result was the amount of support went very far down, and so the rate of progress ground to a halt. If we had continued on the curve we were on in the 1980s, we might have succeeded by now. But we've been held back now for 20 years by reticence from the major funding agencies to support this kind of project in a big way.
You've got to accept that it's a fair, I wouldn't say criticism, it's not a criticism, but it's a different way of looking at this problem, because at the end of the day, we haven't heard from anyone.
That's right.
Where is everyone?
That's a fair challenge. Of course, it's known as the Fermi Paradox because the great physicist Enrico Fermi thought through all of the thinking which is behind all of this business and realized it leads to the idea that there are many civilizations in space and that they've become very advanced, and he would expect that some of them would have embarked on space travel and visited here, or perhaps even colonized the Earth. And as far as we can tell, it hasn't happened. And does this mean that this never happens? Because it only takes one to do this, to perhaps colonize the whole galaxy. And it only takes tens of millions of years to colonize the whole galaxy if you are of that mind. And it hasn't happened. So does this say maybe we are alone after all? This is the Fermi Paradox. And my answer to that is that we have been misled by what takes place in science fiction movies and books, where it's it's just assumed that the more advanced civilization finds it easy and inexpensive to travel across space at high velocity and go from one star to another. Well, if you actually take some serious physics and simple physics and analyze such a situation, you discover it's not easy at all, no matter how sophisticated you are. And to give you a feel for that, let's just imagine that we had rocket propulsion engines which can get us up to, say, the 10th the speed of light, which, by the way, is about as fast as you can go without being in great danger of being destroyed, because at that speed, if you impact anything...
Yeah, bits and pieces up there, that's going to do you some damage.
Not little damage, big damage, because at the 10th the speed of light, when you impact something, it releases as much energy as though that little piece was a nuclear bomb. It destroys your mission. So all it takes is something a few millimeters in diameter to actually destroy your mission. So probably a 10th the speed of light is the highest that you can go without really being in great danger. Anyway, that's an aside, so to speak. But let's imagine you could go that fast and say, all right, we're going to send a mission to a nearby star, say 10 light years away, which is probably the closest where the star that has a habitable planet, at a 10th the speed of light, and it's going to be a spacecraft about the size of an Airbus 320, and it has 30 or 40 people on it as passengers. What's that going to take? Before we get to that, you might ask yourself, would you want to go? At a 10th the speed of light, to go 10 light years takes 100 years. You're not going to get there alive. And just think of sitting on an Airbus 320 for 100 years, watching the same movies over and over.
I struggled coming over here actually
with just
and my screen was broken, so I couldn't watch any movies.
Well, all the screens would be broken before 100
it was
years.
Okay. I read your book, so it was okay. So I had quite a nice trip.
Okay. So, well, anyway, let's assume you can find enough somewhat mentally ill people who are willing to make this trip. What does it take in the way of energy? Now, the amount of energy in a spacecraft moving at that speed, an A320, can be calculated from the most simple laws of physics. It doesn't require you to understand the propulsion system at all, but you can calculate the total amount of energy, and the propulsion system has to provide that much energy and more to make up for inefficiencies. Well, how much energy is in a spacecraft, an A320 going a 10th the speed of light? Well, it turns out to be equal to the total electric power production of Europe for 200 years. 200 years! Yeah. You would have to shut down Europe for 200 years to launch this mission. And by the way, that only gets it up to speed. It doesn't provide any way to stop it when it gets there. Yeah. And so the energy requirements are enormous. And they are so great that there's nothing that would be retrievable or collectible from another star system or planet that would justify that expense. There's no way one civilization can exploit each other. There's no information that would be worth all of that, particularly since you can gain that same information through radio searches, presumably. And so the reason they haven't come to us is simply that they are intelligent, and they have worked through what I just described to you and realized that it's a foolish, incredibly foolish enterprise to embark on. The only ones who might have tried it are ones that are foolish and stupid, and they don't know how to do it, so they haven't come to us.
But aren't we thinking about these in terms of our own technology now? I mean, back in 1960 when you did the original search, you know, we're looking for these intelligent civilizations with our current technology, and now of course we've moved on and we're thinking about it in terms of our technology now. So in terms of explaining the Fermi Paradox, aren't we thinking about it in terms of, you know, when we talk about 200 years of electricity in Europe, perhaps they've developed new forms of collecting energy, whatever that may be.
Still
exotic forms, matter-antimatter or Dyson spheres or...
Still, it's a great deal of energy, and there's a better way to use it. Yeah. For example, to my mind, the sensible thing to do if you really want to exploit space is to colonize your own planetary system. The cost of establishing a colony in the solar system is about 1/1,000,000th the cost of establishing that on a nearby star, when you take into account the transportation costs. there is enough energy coming from the sun that if you captured it all, as in Dyson spheres, it would support 10 to the 22nd power human beings. So that is, presently our population is about 10 to the 10th human beings. So this would be 10 to the 12th. That's a million times, not a million more people, but a million times more people than we have today. That sounds like enough.
Yeah.
And you can do it with resources that are available in your own system from the asteroids and things like that.
But even if we haven't, obviously, you know, despite what people may think they see or believe happens, other civilizations haven't come here. Why haven't we been able to detect them? I mean, forget about space travel, but
why aren't we detecting? That's easy. We just haven't tried enough. We, I think, have again been misled by unfortunate, exuberant claims by myself and other colleagues that we've done a lot of searching, and we haven't. We've looked carefully at only a few thousand stars on a very small number of the channels that are possible in the electromagnetic spectrum, and that's just hardly even a start. If you take perhaps reasonable or even optimistic values for the factors that go into the equation, it suggests that right now there are maybe only 10,000 civilizations we can detect in the galaxy. That's 1 in 10 million stars. We have to look at 10 million stars, and before we have a good chance of succeeding, we have a long way to go.
So it's needle in haystack.
It's a needle in a haystack, and we've looked at only a few little handfuls of straw.
But I guess the problem with needle in haystack, we're not definitely sure there is a needle in there. We believe there to be a needle in the haystack.
Yes.
And so how much of this search comes down to ultimately a degree of faith in the fact that...
Well, yes, there is faith, and it has... The thing that requires faith is that civilizations will remain detectable for a substantial time. We ourselves have been detectable for about 100 years. We may or may not be typical. We are in the process of becoming less detectable through advancing technology. On the other hand, there are potential technologies which will keep us detectable, such as solar power stations in space. So there's a very important unknown future of technology for civilizations like ours, which greatly impacts the length of time they are visible, and we don't have a clue as to what that is. So for the present, all we can do is search, and it doesn't cost much.
If we carry on searching and we make contact with another civilization, what will that do for humanity?
What that will do for humanity is probably beyond anything we can imagine. As in many things, the result of a discovery produces results which are far different from what was predicted. What we can predict, of course, is that we will learn of how intelligent other creatures may be, what evolution can lead to, how far we might evolve. We will find out things such as, do we develop a means to connect computers directly into our brains and become, in a way, partly cyber creatures. We will learn if other civilizations colonize space. We will learn what their art forms are. We will learn of what they enjoy, what the sources of joy are with other intelligent creatures. And we will learn perhaps of what doesn't work, what to avoid. Maybe colonizing space is a bad thing. We will find out, and it will save us the trouble of learning the lesson through our own through some very difficult and damaging enterprise.
Now, obviously, we're doing the same observation that was done 50 years ago. How much more powerful is this telescope, just in terms of numbers of channels and that sort of thing?
First project had 1 channel. This one has 120,000.
So it's a little bit better, just fractionally.
And this one has 160 times the sensitivity due to the larger dish and the much better receivers of today. And what that means, and this is a good number to have in your show, what took 2 months in 1960, and which only produced data for 7,200 channels, will produce data of equal quality for 120,000 channels in 4/10 of a second.
So 4/10 of a second is the same amount of work as 2 months' work.
Yes.
So 4/10 of a second, and back home in time for tea and cake.
Yes,
Absolutely.
except for that's not what we're going to do. We're actually going to observe for 5 minutes. 5 minutes,
Okay.
which is 300 seconds. That and the sensitivity increases as the square root of that number. Is that right? 5 minutes is 300 seconds. So that's 600 times the original thing. So the sensitivity is increased by the square root of 600, which is 25. And so what the 160 becomes 25 times greater, whatever that is.
It's better, basically.
Lots better.
Can I just ask you about those stars? I mean, here we are 50 years later looking at the same two
Yeah.
stars. Apart from obviously the sort of anniversary,
Yeah.
does it make sense to look at those two stars?
Yes, because they are very similar to the sun. I've got all the data here if you're
Here we go. On your napkin.
But there has been studies by people who try to identify stars which they think are likely to have habitable planets. Now that's a dicey business. They don't take it too seriously. But there is a catalog called the HabCat catalog, which is the Habitable Stars catalog. And there are 5 stars in that catalog that are considered the prime candidates, and 2 of them are these 2.
Wow. And did you know that at the time?
No.
So was that a wild guess
It was-
based on that they're
were-
sun-like stars?
Those were chosen because they were the closest sun-like
Right,
stars.
yeah.
And nothing to do with this HabCat gets into things like apparent age of the stars, which you can judge from the intensity of the iron lines in the spectrum, the amount of dust and debris around them, which we now can directly observe, and additional data like
Yeah.
that.
Okay, 4 seconds.
Sorry, yeah.
Okay,
Okay,
and
now
that-
we're looking at the star.
Yeah, we're not taking data yet because we're
Yeah.
balancing things again, but
Yeah.
it'll just be a few moments.
How do you feel sitting here looking at this, doing this
A
again?
lot better than I felt 60 years ago, 50 years ago, because all we had then was a pen and ink recorder.
So we've got the telescope now is trained on Tau SETI, and we're starting to get in. Is this data coming in?
Yes.
What is this, the first?
We're starting to get the first data in now from Tau SETI. Frank, so what's so we're done observing? What's the
We've
the
done
news?
taking the observations.
Yeah.
We still haven't. We took a close look at the conspicuous spikes in the first 3 sets of data we took and saw nothing that looked like an extraterrestrial signal.
Mhm.
We've got 1 pair yet to look at.
Right.
Dealing with the deluge of data right now is what's going on.
And how do you feel about it? Are you sort of disappointed?
No, it's like buying a ticket in the lottery. If you're going to be disappointed that every ticket loses, you shouldn't be in the business.
I know. Only because it's, it's redoing the original search, but with so much more sophisticated
Yes.
equipment.
Yes. It
So I'm just
just
wondering
showed
how you
that,
feel about that.
It just confirms what the original search found, that there's, from these 2 stars, nothing coming in a very narrow 12 megahertz piece of the radio spectrum. But that's a small piece of the radio spectrum. We haven't exhausted the potentialities of these stars as sources of signals.
Yeah.
We looked at the so-called magic frequencies, which are a very anthropomorphic choice.
So let's just so while we were looking at the so-called water hole, which is like you
Yes.
said, this anthropomorphic choice.
Yes.
This is where we would like to think that people
Yes,
would be broadcasting.
We like to think that they think like us
Yeah.
and are choosing to broadcast, which we don't do.
Mm.
And in fact, it's illegal for us to transmit in the hydrogen
Right.
line spectrum because that's a protected frequency for radio astronomy.
Right.
So that's why we looked at the OH, because that's also a water hole. That's actually protected too, though, by us. But maybe the extraterrestrials don't protect these things.
Yeah. Can you ever do you think you'll ever get to a point where you'll say, okay, this haystack is just too big?
No, because this particular spectrometer we were using was not designed for SETI, and so it is quite limited. It's limited in its overall piece of the spectrum it looks at, and it also is limited in its bandwidth to what to us is broad bandwidths. We like to look with 1 hertz bandwidths because a very clean signal from a transmitter does occupy only 1 hertz. And if you can match your receiver to the bandwidth of the transmission, you have much better sensitivity. If they were really trying to contact us, they'd use very narrow signals, about 1 hertz. You can't go narrower than that, by the way, because the galaxy, as the signal travels through the galaxy, the signal gets broadened a little bit. Thank goodness, because otherwise we'd have to look for a millionth of a hertz bandwidth or something. It would be awful. But 1 hertz is about as minimal as the bandwidth can be, just because of galactic electrons.
That was a really weird experience. Not at all what I imagined. I think in my naivety I expected people to be running around and excited and champagne corks going and listening, but it was really quite sort of utilitarian, and I was surprised by the technology seemed to be the focus, people fiddling with computers and computers not working. And also I noticed a real sort of change in Frank. He seemed really quite deflated. Earlier on when we were chatting, I got that infectious optimism, especially when we were showing him around the old telescope and he was back in that room for the first time. You just felt his passion, still 50 years on, and suddenly it just kind of went. And I guess that's the weird thing, having been doing this search for 50 years and finding nothing, keeping that faith has got to be a really difficult thing. And it just highlights the fact that it's more than just a science question. It's a question about being a human being. And it's a question about keeping the faith. He said a really interesting thing, actually. He talked about it. He said looking at Tau Ceti was like buying a lottery ticket. Looking at Epsilon Iridium was like buying a lottery ticket, like buying 2 lottery tickets. But it's a lottery where you just assume there's a jackpot. It's a lottery where you don't know whether there's a jackpot. Buying a lottery ticket is crazy enough as it is, but buying a lottery ticket where you don't know whether there's a jackpot takes even more faith, I guess. The interesting thing is, because it's a 50th anniversary, and I suddenly realised there's another anniversary because you've got a birthday coming up. And I heard a really terrible thing, which was that you'd never read Douglas Adams's Hitchhiker's Guide to the Galaxy, which is probably certainly my favourite and most reached for book. So just to say thank you for spending this time with us. I managed to source a copy for you.
Oh my goodness.
And I hope you enjoy it.
Oh, thank you very much. Now I can find out what I've been doing all these years.
Exactly. Anyone searching for N, I think, should certainly read that.
Oh, good. Oh,
there you go. But thank you very much for spending the time.
Thank you very much. That's nice. That's very nice. Oh, thanks.